So till now we have completed 3 experiments, the design part of the 3 experiments, and all the 3 experiments are related to the digital part. So the first experiment was related to half adder, full adder, half subtractor and full subtractor, and the second experiment was about a binary to gray and gray to binary, that is a code converter, and again the third experiment is related to the MEV technique. So I hope you are clear with all the 3 experiments in design part. So now we will enter into the analog part, the first experiment. Okay, the first experiment in the analog part. So what is the difference between this analog and digital is? So let me not go in depth because in the theory classes itself I have explained what is analog and what is a digital and all. So coming to the practicals. So the digital means you will be using the experiments that whatever we have discussed till now, that is all about a digital part. So you will be using a digital kit. I will be showing in the video about that as well a little bit later. So let me complete the design part first. So there will be a digital kit. Okay. So you will be using a wires in order to give the connections and to check the outputs. So that is a digital part. So this analog part is nothing but you will be feeling the components. That is the resistors, capacitors, op-amps and wires, and how to give the power connection, how to connect it for ground, how to short some of the points. All those things you will be connecting in a single board, and that board is called as a spring board. Okay, so if you want to chop the vegetables, where you will be chopping, you will be using some platform, right? What platform you will be using? You will be using a chopping board. Similarly, if you want to design any of the circuit, okay, or if you want to solder something, or if you want to build a circuit, then you require some board. That board is called as a spring board. Okay, that board is called as a spring board. Why it is called as a spring board? Because it will be having n number of springs. Okay, if you are putting a wire into it, it will be tightly fitted. So therefore, there will be n number of spring points. I will be showing all those things in the implementation part. Okay, still I am doing only the design part. We will come back to the implementation, and at that time I will show how the spring board will actually look. So the next generation after the spring board, we are using the breadboards. Okay, we can implement the circuit either in the spring board or in the breadboard. Okay, I'll explain in the videos that thing. So right now we are understanding the fourth experiment or the first experiment in the analog part. So what is the experiment name? Using mu A. This is not M, this is mu. Okay, this is mu A 741 op-amp design 1 kHz relaxation oscillator with 50% duty cycle. All the terms are very new to you. I hope you have not understood the title of the experiment. I'll just explain. Listen very carefully. So what they are telling, using the op-amp, design the oscillator which is having the duty cycle of 50%. It means what? You have to design what? You have to design the relaxation oscillator. So first of all, what you have to use in order to design this? They are only telling using the op-amp, and the op-amp IC is what? MUA741 op-amp. Okay. So now using this op-amp, you are supposed to design the relaxation oscillator, and you don't know what is meant by relaxation oscillator. I will tell all those things. Okay, you have to design the relaxation oscillator, and that oscillator should give a duty cycle of 50%. So you don't know what is meant by a duty cycle also. Okay, fine. Leave all those things, but keep in mind what is the experiment. You have to design what? You have to design an oscillator. What the name of the oscillator? Relaxation oscillator. By what? Using what you have to design this oscillator? You have to design the oscillator by making use of an op-amp. So you know what is meant by an op-amp. Op-amp is nothing but the operational amplifier. So in the first unit I have just given a brief idea about what is meant by an operational amplifier, right? So now we have to design the relaxation oscillator by using the op-amp. Okay, we'll come back to this duty cycle a little bit later. Okay, so what is meant by an oscillator? As the name specifies, oscillator is nothing but it generates the oscillation. So what type of an oscillation? Whether a sinusoidal oscillation or a square oscillation. Okay, so I'm just giving the definition of an oscillator. So oscillator means it generates the oscillation. So it can be either a sinusoidal oscillation, or it can be either a square oscillation, or it can be a triangular oscillation. Okay, an oscillator is nothing but to generate the signals in the form of oscillation. That's all. Now coming to the relaxation oscillator. So the relaxation oscillator, which type of oscillation it will generate? It will generate a square wave. Okay. the output waveform that it is coming from your relaxation oscillator. So what type of oscillation you are getting from this relaxation oscillator? You will be getting a free running. Free running means continuously running square wave or square oscillation. Understood? So I hope you have understood what is meant by a relaxation oscillator. Oscillator means what? It generates a oscillation. It can be either a sinusoidal or triangular. Sinusoidal andre gottalla. Sinusoidal means this is the sinusoidal. So it can be either a sinusoidal or triangular or square. But we are designing what? We are designing the relaxation. Hence you will be getting a square wave. Okay. So you are the output from the relaxation oscillator is a square wave. So that's what I have written here. Okay. Now you just observe the first waveform. Fine. Okay. So now you have got a brief idea what is meant by an oscillator and what is a relaxation oscillator. Please take down the definition of an oscillator and relaxation oscillator, and please take down whatever I am telling, all the important terms. You keep writing in your observation book. Fine. So now what I am telling you, have to design this. Okay. You have to design this relaxation oscillator by making use of what? By making use of an op-amp. Okay. What op-amp? You have to use a MUA741 op-amp. So since you have to use a MUA741 op-amp, let me write down the pin configuration. So this is the pin configuration. So pin configuration, okay, pin configuration of MUA741 op-amp. So how many pins are there in this 741 op-amp? So there are 8 pins. 1, 2, 3, 4. 4 towards the left side, 5, 6, 7, 8 towards the right side. So now we will understand what are all the pins and what are the details related to the pins. So the first pin and the fifth pin are offset null. It means we are not that pin is not being used anywhere else. Okay. First pin and fifth pin is not used. Okay. Next. Second pin and third pin are the input pins. So now second pin is called as what? Inverting input. I think it may not be visible properly. Please check out. The second pin is inverting input and the third pin is non-inverting input. So both are inputs. First is inverting and the second pin is inverting and this third pin is non-inverting pin. And this fourth pin should be always given to the negative power supply. Okay, we have to give it for negative voltage. Next, seventh pin should be always given to negative positive voltage. Next, eighth pin is not connected, we are not using that, and you are extracting the output from the sixth pin. Okay, so this pin configuration, there is no need to by heart it will be given in the exam. Okay, whenever you want to implement this particular experiment, so this pin configuration will be given in the practical exam. Okay, first is offset, fifth is offset, and eighth is not connected. Sixth is output. 2 and 3 are the inputs. Second pin is inverting and the third pin is non-inverting. I just tell what is the inverting and non-inverting. Seventh is should be always connected to the positive voltage, and the fourth should be always connected to the negative voltage, and you are extracting the output from the sixth pin. So now this is the symbol of the op-amp. See here, second pin is what? Inverting input, and third is non-inverting input. Inverting input andre negative terminal. Okay, see here, inverting andre negative terminal, non-inverting andre positive terminal. Okay, these are the two terminals that are acting as an input. So second and third. Seventh you have to give it for positive. See here, seventh I have to give it for positive, and fourth I am giving it for negative, and you are extracting the output from the sixth. So the op-amp diagram is there. So totally 2 inputs, 1 output. So power supply means positive voltage 7th kodbeku, negative voltage 4 ge kodbeku. So totally 1, 2, 3, 4, 5. 5 pins you are using. The rest 3 pins you are not used, that is 1, 5 and 8. Those pins we are not using it. So this is the symbol and this is called as an op-amp. So what is an op-amp? It will be just amplifying your signal. Amplifying means what? So for example, your signal is only this much strength. Okay. So now if I pass it through the op-amp, your signal will become like this. The amplitude, okay, the voltage level will be increased whenever you are passing the low level signal to the lower level signal into amplifier. So as the name itself specifies, op-amp is nothing but the amplifier which will be amplifying or increasing the voltage level, this one to this level. from this level to this level. Don't go in depth. For computer science students, this much is enough. Okay, op-amp andre it amplifies. So signal strength kadme idre adana signal strength na increase madikoskara we are using a device or a component called as an op-amp. This much it is enough for you. So now using this op-amp you have to design a circuit in order to get what? A square wave. Okay, so you are designing the circuit. So how to design the circuit? So designing the circuit andre resistors connect ಮಾಡಬೇಕು, capacitor connect ಮಾಡಬೇಕು. So here there is a feedback resistor. So why it is called as a feedback resistor? Because so this resistor is connected between the input and output. So therefore this resistor is called as a feedback resistor. So how many resistors you are using in your circuit? Totally 3 resistors. See here R1, R2 and here 1. That is a feedback resistor. And this is a capacitor. So what is a resistor and capacitor? So resistor means we should not go in depth again because I will be explaining the same thing in the implementation part also. So the resistor is nothing but, so this is the resistor, so which will oppose the flow of current. Okay, which will oppose the flow of current. So in the pipe, if water is moving very forcefully without any obstacles, then it means that the resistance is very low. Okay, in the same thing, in the same concept, in the same line, if the current is flowing very easily without any obstacles or without any resistance, then we can call that the resistance of that particular circuit is very low. So if the resistance is very high, then the current cannot pass through that particular wire. So I hope you have understood what is meant by resistor. Resistance means it just opposes the flow of current. So now what is a capacitor? Capacitor will hold the charges. Okay, capacitor holds the charges. So this much is enough. We should not go in depth. Okay, capacitor holds the charges. Resistance means it opposes the flow of current. So this much is enough for you. So now, so we have to design the circuit diagram. Okay, so you have to implement the circuit diagram in the springboard. Andre op-amp connect ಮಾಡಬೇಕು. Then you have to connect the resistors. So resistor is there, 3 resistors there. So you have to take these 2 resistors and you have to take one capacitor. So what type of a capacitor you have to take? You have to take a 0.1 microfarad. So likewise, you have to keep in your mind. Okay, you have to keep in your mind what are the values we are using. So now I told that I have to design it, right? So if you want to design, what is meant by designing? So you have to get the value of this feedback resistor. So if you are getting the correct value of the feedback resistor, then only you will be getting the square wave. So how to get this value? So to get that value, we have to use some of the formulas. So this is not a derived formula. Okay, we are not understanding the derivation. We are just taking the formula which is already ready for this particular relaxation oscillator. So this formula use ಮಾಡಿದ್ರೆ ನಿಮಗೆ square wave ಬರುತ್ತೆ. So that type of a formula is already there. Okay, we are not deriving it. So what is the formula? T, capital T is nothing but the time is equals to 2 into resistance into capacitor RC, natural logarithm ln. Okay, ln of 1 plus beta by 1 minus beta. Okay, beta andre special symbols. Okay, so this 1 plus beta and 1 minus beta. What is beta? Beta is nothing but the formula is given as R1 by R1 plus R2. So what I am assuming it, so this one you can assume it. So you can assume these resistors like this only. You cannot use a different value. You cannot use 5K. If you are using 5K, then again this feedback resistor value get changes. Okay, I will just come back to that. So right now what I am assuming R1 and R2 as, R1 I am assuming it as 10K and R2 I am assuming it as 10K ohms. And again the unit for resistance is ohms and it is written like this. This is the symbol or this is the unit for resistance. Kilo means what? 10 into 10 to the power of 3. So this is the thing what? 10 into 10 to the power of 3 ohms. Okay, 10 kilo ohms. So this R1 and R2 we are assuming it, and we are also assuming the capacitor as what? 0.1 microfarad. So farad is the unit for, say if you want to purchase or if you want to purchase a milk or water, what is the unit for that? it is a liter. If you want to purchase any vegetables, we will be using a unit called kgs. So likewise, if you want to measure the capacitance value, you will be using a unit called farad. If you want to measure the resistance, you will be using a unit called as ohms. Okay, this is ohm. 10 kilo ohm, 10 kilo ohm, 0.1 micro. Micro means 10 to the power of minus 6. All these things you have to keep in mind. Okay, these are all some new terms. Kilo under 10 to the power of 3. Micro under 10 to the power of minus 6. Okay, so we are getting a very small capacitance value. So now we will just substitute the values of whatever we have assumed and we will get the value of feedback resistance. So what is the beta value we get now? What is the beta value? So I have already assumed my R1 is equals to 10, R2 is equals to 10. So 10k by 10k plus 10k. So what will be our answer? 10k by 20k, no? It is 10k by 20k. So beta is equals to 10k divided by 20k. So kilo get cancels. So 10 by 2 is nothing but half. That is equals to 0.59. So my beta is equals to 0.5. So now I have to get the value of resistance. Okay, R is nothing but this one. Okay, now I have to get the value of feedback resistance. So I have the capacitance value and I got the beta value and my T. T is nothing but 1 millisecond. I am assuming that as well. So T is equals to what? 1 millisecond. So now I will just take R towards my left side. I will rewrite my equation because all the terms are available. I have to just find the R value. That is the feedback resistance. So if I am writing like that, so 2RC ln of 1 plus beta and 1 minus beta is what? 1 plus beta, that is 1.5 by 0.5. 1.5 by 0.5 is 3. So I write it as 3 here. Okay, is equals to T. Okay, R I will keep it towards my left side. R is equals to T divided by, okay, ln of 3. Okay, ln of 3 into what? 2 into C. 2 into C. Now just substitute. T is equals to 1 millisecond. 1 millisecond divided by ln of 3 into 2 into 0.1 microfarad. Okay, so this is what this is. If you are substituting whatever the values that we are assuming, so you get the resistance. You can use the currency 1 millisecond under 1 into 10 to the power of minus 3. Okay, I repeat once again. Milli means 10 to the power of minus 3. Micro means 10 to the power of minus 6. Kilo means 10 to the power of 3. So now you have got the resistance as 4551.19. So that is nothing but I can approximately write it as 4.5 kilo ohms. Okay, kilo means 10 to the power of 3 now. So therefore 4551 resistance value. So you are getting it as 4.5 kilo ohms. Now I have to use this 4.5 kilo ohms here. Okay, I have to use 4.5 kilo ohms in my feedback resistance. Okay, so this is the circuit diagram for the relaxation oscillator. So if you just observe, I am using the op-amp here. So second terminal is connected to the capacitor and the third terminal is connected to the 2 resistance, that is a non-inverting terminal, and one more feedback loop is coming, that is from output to input back, and we are trying to find the value of the feedback resistor. So how we have found the value of feedback resistor? By using this formula. Okay, understood? So no need to worry. E formula ಹೇಗೆ ಬಂತು, ಈ circuit ಹೇಗೆ ಬಂತು, don't worry. Okay, ಅದೆಲ್ಲ that is already designed. So relaxation oscillator circuit is this one, and the derivation for this is the formula for this is T is equals to 2 into RC natural logarithm of 1 plus beta divided by 1 minus beta. So this formula you have to keep in mind, and beta is nothing but R1 divided by R1 plus R2. So in this circuit diagram, what are the things that we have assumed? R1, R2 and also 0.1 microfarad capacitor and also T. T is equals to what? 0.1 millisecond. What is T? So one cycle length, one cycle time duration is to. So what is the waveform or what is the characteristics I have written is? So this is the output that you have to generate it. Okay, from this circuit. Okay, so this is, so why I am assuming that t is equals to 0.1 millisecond is, so one duration, so this is one complete cycle from this point and this point. So one complete cycle is one to t on one to t off when one is rising and one is falling. So one cycle should consist of one rising edge and one falling edge. So t on and t off. So this is one complete cycle. So this one complete cycle I am assuming it as 0.1 millisecond. So what is this complete cycle? This is also 0.1 millisecond. Okay. So 0.1 millisecond, 0.1 millisecond, 0.1. You are designing the waveform however you want. If I am taking t is equals to 0.2 millisecond, then your one cycle will be this much length. Okay. So your waveform just look like this. Your waveform will just look like it is so big. It is 0.1, sorry, it is 0.2. So in order to get a correct or a clear waveform, so I am considering my time is equals to 0.1. Okay, and now we shall also discuss what is meant by the duty cycle. Okay, what is meant by duty cycle. So please take down all these things. I just erase this part. Okay, I just erase this part and I will explain what is meant by a duty cycle. So please take down. So we are what is this design is used for in order to get the value of this feedback resistance. So this is not so important. Okay. So you can assume anything in the sense, you cannot take 5 k ohms, 4. You cannot assume like that. You have to take 10 k. So the main important design is to get the value of the feedback resistance. Okay. So what is this? What is this? So this is the waveform that you will be getting in the part of capacitor. If you keep output in the commando wire now, if you are keeping near the capacitor, then your waveform looks like this. See here, I am just written a dotted lines. Okay, to the rising edge and to the falling edge, to the rising and to the falling edge, I have written the dotted lines. So whenever there is a falling, it will be falling. So during the off cycle, my waveform is falling, and during the on cycle, my waveform is rising, falling, rising, falling, and rising. So when it is falling, whenever it is in the off period, when it is rising, whenever it is in the on period. So that's why I have written the dotted lines. If you are not writing the dotted lines, then it will not be having a proper synchronization. So therefore, in order to represent the waveform very neatly, okay. So in order to have the synchronization between this and this, I have written the dotted lines. Right. So let me write down or let me explain what is meant by a duty cycle. So this is the design part. Okay, I hope you have understood what is meant by the design part. So now, so what is meant by a duty cycle? So duty cycle is given by T on divided by T on plus T off. Okay, duty cycle is equals to T on divided by T on plus T off. What is this T on? What is this T off? This is nothing but T on. This is nothing but T off. So this complete is called as what? T on plus T off. Can I call it as T on plus T off? And that T on plus T off is also called as capital T. That is what 0.1 millisecond I have assumed. So I can also rewrite my duty cycle formula as T on by capital T. Okay? T on by capital T. So now what they are asking you to generate, you have to generate a 50% duty cycle. So 50% duty cycle means, this should be 50%. Duty cycle 50% you will be getting the waveform like exactly like a square wave. Okay, exactly like a square wave. T of 50% to T of 50%. T of 50, T of 50. So in case in the exam, if they are asking, they will not ask, but I am explaining the concept. So if your duty cycle is 75%. So T on will be 75 and T off will be 25. T on will be 75 and T off will be 25. So this is a 75% duty cycle. This is a 50% duty cycle. So 25% duty cycle they will have. So T on will be 25 and T off will be 75. T on will be 25 and T off will be 75. So this total T will be what? 100%. Understood now? So duty cycle means what? So T on and T off will be exactly 50 and 50. Okay? So now if they are asking you to do it for 75, then T on will be 75 and T off will be 20. So this is what I on divided by capital T, and the capital T is nothing but T on plus T off. Okay. So now how I have written the waveform? See, this x-axis, writing the x-axis and y-axis is very important in the case of the characteristics. So this x-axis is always T and the time. Okay, x-axis is always T and this y-axis is voltage. So this is the output voltage which is represented as V0, output voltage, and this is the capacitor voltage represented as Vc. Okay, you have to write all these waveforms in the graph. All those things will be a next concept that I will be teaching you whenever I am explaining about the implementation part. So this is the design part of relaxation oscillator. Very fastly let me briefly explain what is an oscillator and what actually you are doing in this experiment. So in this experiment, we are designing the relaxation oscillator by making use of a 741 op-amp. So what is meant by relaxation oscillator? It generates a free running square waveform, and in order to design this relaxation oscillator, we are using one formula, that is capital T is equals to 2 into RC, natural logarithm of 1 minus beta by 1 plus beta. And what is beta? Beta is nothing but resistance R1 by R1 plus R2. By using those two formulas, we are getting the value of feedback resistance by assuming some R1 capacitor and also by assuming T value. So this is the outputs that you are getting whenever you are keeping the point at 6 and whenever you are keeping the point at 2. Whenever you are keeping the output wire at 6, you will get this waveform. Whenever you are keeping the output wire at 2, you will be getting this waveform. Okay, don't worry about the implementation. I'll just make a different video for that little bit later. Now try to understand the design part for all the experiments. I hope you are clear with all first 4 experiments. Okay, we'll just go to the implementation little bit later on once the design part is done for all the experiments.